Okay, we can start our next seminar. And today our speaker is Professor Giuseppe Rosario Mingione from Parma. Please.
Okay. Thanks a lot for this invitation. It's always a pleasure to be here in company of my St. Petersburg friends. And okay, nonlinear potential theoretic methods in nonuniformly elliptic problems. So this talk is about some new approach on let's say optimal regularity of solutions to elliptic and also parabolic equations, and minimizers of functionals of the calculus of variations that guarantee to this kind of approaches guarantee the optimal regularity of solutions in terms of the given data. So the assumption, I'm going to consider equations of this type, where the main emphasis is that I want to prescribe the minimal conditions on mu and on dependence on x in order to get Lipschitz continuity. And the main focus is on non-uniformly elliptic operators. Okay, let me consider first the classical setting of Lagiszewska and Dure-Altseva, and in particular, I will consider uniformly elliptic operators. And these are the assumptions I'm going to consider, and they are modeled after the classical P-Laplacian operator. So these are the assumptions that I'm going to consider on these kinds of operators, and eventually I'm going to say something about the dependence on x. Okay, so in particular, the classical P-Laplacian operator satisfies these assumptions that are in fact modeled after the P-Laplacian operator. Okay, under these assumptions, when P is equal to 2, so you have a sort of nonlinear Poisson equation, then there's a first gradient bound obtained via Riesz potentials that has been obtained by me several years ago. This is a curious bound because it tells that you can pointwise bound the size of the gradient of solutions in terms of the Riesz potential of the right-hand side. In particular, when you have good decay, when you are in the whole Rn and you have good decay properties at infinity, so you get this pointwise bound that tells you that, this bound is classical for the Poisson equation, and it goes via fundamental solution. Here, the novelty is that you can get the same bound for any nonlinear equation of this type. So in particular, you skip the use of fundamental solution. So this is a first example of how linear and nonlinear potentials can be used also in the nonlinear setting. Okay, this was obtained by me several years ago, and then we surprisingly enough extended to the case, to the P case, to the P-Laplacian case in these two papers with Frank Dosar and Tuomo Cusi, and they tell you that amazingly enough, the same holds for any general equation with P growth. With P growth, so in some sense, this kind of estimate, in a sense, completely linearized the regularity theory up to the Lipschitz continuity, in the sense that you can that anything that is known for the Poisson equation extends really to the P-Laplacian type equations because you have this bound. So you can in particular prescribe the best possible conditions on mu, guaranteeing the local Lipschitz continuity and these pointwise estimates for solutions independently of P. This was something that was actually, that I heard was conjectured by Nina Realtseva many years ago, that the kinds of assumptions you have to prescribe on the right-hand side in order to guarantee Lipschitz continuity are independent of P. And this is completely independent. This is an estimate whose right-hand side is completely independent of P. Therefore, anytime the Riesz potential is locally bounded, this guarantees that the gradient is locally bounded. We did this under this condition, and then eventually this was extended to this case by Nguyen and Cook. And in the vectorial case, this remains true for the P-Laplacian system, and this has been proved by Tuomo Cusi and myself in 2018. And okay, in particular, you can allow for a completely intrinsic formulation of this result using the coercivity of the vector field A of du, and you can reformulate this last estimate in a completely intrinsic way, telling that exactly in the case of the Poisson equation, whatever is under the sign of divergence can be pointwise bounded by the Riesz potential of the right-hand side. And this statement is P independent. Now, this is even more, this is not even, linked to the P growth condition, because there's this nice theorem of Paolo Baroni that tells that if you consider this general uniformly elliptic equation, where uniform ellipticity is prescribed by this condition that you read at the bottom, then you can tell exactly the same. I mean, so it is actually a general fact of elliptic equations in divergence form. Whatever is under the sign of divergence can be pointwise estimated by the Riesz potential of the right-hand side, plus, of course, a localization term, as it was the Poisson equation. So there's no difference between Poisson equation and any non-uniformly and any uniformly elliptic equation. So this is as long as gradient estimates can be obtained by Riesz potentials and also nonlinear potentials of the right-hand side. So let me just briefly exhibit an application of this. Okay, this is a very classical theorem of Stein. Okay, you know that if dv, if you have a function v whose gradient belongs to ln plus something, then v is Hilbert continuous by Sobolev-Murray embedding. Now you wonder, what is the limiting space guaranteeing that this kind of inclusion implies that v is continuous? Not necessarily Hilbert continuous, but just continuous. This is answered by Stein in a classical theorem from 1981, and this is the Lorentz space Ln1. Lorentz space Ln1 is described saying that the level set of G decay fast enough at infinity in order to get this pointwise this integral to be finite. And an example of a Ln1 function is given by adding a log to the usual powers. So the second index is actually turning the first one, and it's bound to correct powers with slider growth conditions like logs, for instance, or power of logs and so forth. So they are borderline cases in this sense, in this respect. So they are borderline cases in this respect. And okay, now a standard application of Stein's theorem is the following one. Lorentz spaces are interpolation spaces. So if you combine interpolation theory with Calderon-Zygmunt theory, you come up that if the Laplacian of a function belongs to Ln1, then the whole Hessian of the function belongs to Ln1. So the second derivatives, the full second derivatives, belong to Ln1. As a result, you obtain the continuity of the gradient, and this is actually an essentially equivalent reformulation of Stein's theorem. This result is sharp, as proved by Chunky in 1994 by a counterexample. So now the point is that the previous estimates come along in a scheme that allows to guarantee that Stein's theorem is a perfectly nonlinear fact. In fact, what we proved with Tuomo Kuusi is that if the divergence of any general uniformly elliptic potentially degenerate operator belongs to Ln1, then the gradient is continuous, again, as it was the Poisson equation. So, and how this can be obtained? This can be obtained by simply observing that the gradient is continuous once the convergence to zero of the Riesz potential of the right-hand side is uniform with respect to x, and this is implied by Ln1. So this introductory part was to say the basic role of ln1. ln1 is in a sense a universal space guaranteing Lipschitz continuity in the uniformly elliptic regime. This is what you get. Okay, now I'm shifting to the non-uniformly elliptic setting. So the first part was just to remind what happens in the uniformly elliptic case, which is in some sense closed. Okay, now I'm going to consider the setting of integral functionals of the calculus of variations, because for non-uniformly elliptic problems, this is more natural. And also, once again, equations of this type that are this time non-uniformly elliptic. And of course, the catch is given by the Euler-Lagrange equation. Okay, ellipticity in our setting means that you can bound the lowest and the highest eigenvalues of the first variation equation with two functions that are g1 and g2. And these are positive and non-negative functions that are bound to describe the behavior of the lowest and the highest eigenvalue. And the same happens for functionals. And in the autonomous case, you can also skip. When there is no dependence on x, of course, you can skip the dependence on x anywhere. So in our setting, non-uniform ellipticity means exactly this. Actually, ellipticity means this. So we are going to assume these assumptions everywhere. So non-uniform ellipticity means that the ratio between the highest and the lowest eigenvalue is essentially bounded when z goes to plus infinity. Why when z goes to plus infinity? Because z is the gradient variable, and we are interested in proving that the gradient is bounded. So we are interested in excluding a bad behavior when the u is large, and therefore we only want to examine the equation when the gradient is large. So uniform ellipticity means that this ratio between the highest and the lowest eigenvalue remains bounded. And this is a crucial assumption in uniform ellipticity, because this ratio appears everywhere when you try to prove regularity estimates for equations. So if this ratio is bounded, then a certain huge number of things can be done. Estimates follow, and everything is okay. So this is the classical uniform ellipticity setting. And the P-Laplacian operator belongs to this setting because the ratio between the highest and the lowest eigenvalue is always bound. And the ratio and the highest and the lowest eigenvalue are both proportional to the gradient, to the norm of the gradient, to the p minus 2. So if this is uniform ellipticity, non-uniform ellipticity is when the opposite happens, and the opposite is when the ratio between the highest and the lowest eigenvalue goes to plus infinity, at least for one point. Okay, in the following, we are not going to talk about what happens for almost every point and giving, fine conditions involving almost every point, because the dependence on x is always considered to be continuous here. So the behavior at one point is already significant. So non-uniform ellipticity, or pointwise non-uniform ellipticity, means exactly this, that for one point, this ratio becomes unbounded when the gradient variable becomes unbounded. This is a classical set. This is a very classical topic, and in particular, it has been a major source of work for mathematicians in St. Petersburg, and probably the best results up to the 80s have been obtained in St. Petersburg, starting by Lagichenskaya and Duraltseva, and there's their book plus a beautiful paper on CPAM in 70. But also on the US side, there were people like Gilbert and Trudinger. In particular, Trudinger's thesis was on that, but also there are classical papers by Ivochkin and Oskolkov, and many people in St. Petersburg work on that. So this is just a number of classical papers. It's a selection, actually. So I'm not pretending that this is comprehensive at any point. And also in the 80s, there's been a lot of thought on this. In particular, there are beautiful papers by Zhikov in the setting of homogenization. There's a beautiful monograph by Ivanov giving a summary of what has been done in St. Petersburg until the beginning of the 80s. And then there are these very, very classical by now papers by Marcellini, who gave a new impulse to the study of these non-uniformly elliptic problems, studying validity of local estimates under very restricted assumptions, and in particular, local estimates, not going up to the boundary, so not using barriers or things like that. And also, people like Zhikov were putting this in the setting of homogenization, elasticity, and Lagrangian phenomenon in the calculus operations. And the most appropriate setting is the variational setting. This is actually the most proper setting, and in this case, the Euler-Lagrange equation works exactly, is of the type we have considered before. And non-uniform ellipticity means that the related Euler-Lagrange equation is non-uniformly elliptic. And this is the variational setting for reasons that are going to be clear later. This is the most appropriate setting for study this type of non-autonomous, non-uniformly elliptic problems. Okay, so if you look at the literature, in a way or in another, there's always one recurrent assumption guaranteeing that the gradient is bounded, the gradient of solutions is bounded. And the assumption is that the ratio between the highest and the lowest eigenvalue is growing as a polynomial of the gradient variable. This is considered everywhere, but in some very pioneering papers by Marcellini, who studied exponential type functions, but I'm going to go back on this later. So as long as the eigenvalues are growing polynomially, the ratio is assumed to grow as a small power of the gradient. And why? Because in a sense, you want to prove that the gradient is bounded. And this can be done easily, or I mean, reasonably, in a reasonably easy way, in the classical way, in the uniformly elliptic setting, when the ratio is bounded. So if the ratio is blowing up, this is an obstruction to the gradient. So there's a competition between the rate of potential blow up of the gradient of the ratio between the eigenvalues and the rate of the blow up of the gradient. So this is resolved by prescribing that the rate of blow up of the ratio is a polynomial with a small power delta. In the setting of integral functionals, if you prescribe that the lowest eigenvalue is growing as p minus 2 and the highest eigenvalue is growing like q minus 2, then the ratio is blowing up as z to the q minus p. And in particular, you have to assume that q minus p is not very far from 0, that is, q over p is very close to 1. These are nowadays called Marcellini's PQ growth conditions, because Marcellini introduced for the calculus of variations in the 80s these conditions for very general reasons, also linked to nonlinear elasticity. And I do not want to enter this because this would take too much time, but it's important that Marcellini studied this systematically. There's also a pioneering paper by Uyaltsev and Udaletova studying functions of this type from 83, I guess. Okay. Now, if you look at Marcellini's paper, you once again find that a condition of this type is essential to prove that the gradient is bounded. Why is it essential? For the reasons I explained you before. Because if q over p is too far from 1, this is always larger than 1, then there could be examples of irregular minimizers. And this already happens in the scala in the autonomous case. So therefore, there's nothing to do, and these assumptions that we have seen before, it's unavoidable as long as you are in the polynomial growth case. And examples of these functionals are clearly, obviously, small perturbations of classical polynomial functionals, like dv to the p log 1 plus dv. there can be functionals exhibiting a different kind of growth depending on the gradient itself. This is an example that I think was first observed by Talenti many years ago in the 80s. This is another example in a way. And then Uraltsev and Urdaletova and people from St. Petersburg in the 80s, they first considered these anisotropic growth conditions where every direction is penalized with its own exponent. Eventually, there's a very beautiful paper by Marcellini who in the 87, I think, that where he has this is a paper by Uraltsev and her students from St. Petersburg, most notably Urdaletova, who also studied several elliptic equations of this type, of non-uniform elliptic type. Okay, so and then there are, non-polynomial growth conditions like this very nasty one by studied by several people like Duke and Hills, Lieberman, Marcellini, and Craig Evans to obtain some approximation of the infinity Laplacian equation. Here, there's a duality here because, okay, theoretically it should be easier to prove that minimizers are Lipschitz because you are penalizing a very, very high growth rate of the gradient. Technically speaking, it's more difficult because the integrand doesn't satisfy the so-called delta 2 conditions. With one exponential and p equals to 2, this was obtained by Lieberman, the gradient boundness, and for any type of composition, this is Marcellini. In a couple of very pioneering papers from 96, 95, I guess. Okay, these are examples of non-uniformly elliptic functionals, and the last one doesn't fall into the previous realm because it has a non-polynomial growth rate of the eigenvalues. Okay, let me give one example, one model example, for which you can, one kind of very simple example, but yet also very significant example. It's a model result obtained by Marcellini by now more than 30 years ago. So you consider this kind of integral functional, and you see that the eigenvalues grows like p minus 2 and q minus 2. For simplicity, I'm not considering the degenerate case here. You can also consider the degenerate case, but let's be simple. So the rate grows, the ellipticity ratio grows like q minus p, and Marcellini proves the following very simple and beautiful theorem together with a local a priori bound. That is, if you assume that this bound holds, then the gradient is locally bounded and you have this a priori estimate. Observe that when p is equal to 2, this is the classical L infinity LP reverse estimate for p harmonic functions. So this is a bound of the type we've seen before. And actually, in the autonomous case, the optimal bound is not known nowadays. So it's not clear what kind of inequality, what kind of quantity you can replace 2 over n by in order to get the best possible bound on the right-hand side. There is actually still research on that. Let me quote, for instance, this recent and interesting papers by Bell and Schaeffner, by Schaeffner and Hirsch and Schaeffner, and also this paper by De Filippis, Christensen, and Koch. And all these bounds are extended and refined. In particular, Bell and Schaeffner, they replaced 2 over n by 2 over n minus 1 for n larger than 2. The only optimal bound is being obtained by Hirsch and Schaeffner, but it's not about the gradient boundness, but it's the boundness of U. And this is optimal because otherwise there's a counterexample in this, I think, 89 paper by Marcellini there, where he proved that U is unbounded under if this condition is violated. So this is the only optimal result known in the autonomous case. So this is just to say that there is activity in this direction. And this result of Bell and Schaeffner is at the moment the best one, I guess, in the general case. Okay, now let me go back to the previous idea. So this is the result that we proved even in the vectorial case for the P-Laplacian system and therefore also for equations. If you have that the divergence of this object belongs to Ln1, then the gradient is continuous and therefore is locally bound. And this is again confirms this old conjecture. I guess it goes back to Nina Uyaltseva, who conjectured that the best optimal, that the optimal conditions on the right-hand side are P independent. And this condition is in fact P independent. Ln1 doesn't feature any appearance of P. So now this is as long as the uniformly elliptic setting is considered. So this condition is universal. We want to know now if this is universal enough to hold in the non-uniformly elliptic setting too. Okay, therefore we go back to the autonomous case. We get the growth conditions of the lowest eigenvalue, of the highest eigenvalue, G1 and G2 respectively. And the assumptions we are considering is that this ratio, G1 over G2, grows as a small power of this quantity. This quantity, it might appear to be a bit odd at the beginning, but it's a natural quantity describing the coercivity of the integrand under the previous assumptions. So the main condition is that the ellipticity ratio, which is by this condition bounded by G1 over G2, then is itself bounded by a small power of this quantity. Okay, and then we have this theorem by Beck and myself, who proves that once again ln1 is a sufficient and at this point necessary condition for the gradient boundaries. We also get it via this apparently awkward a priori estimate, because you see the L during L infinity appears in the upper part of the integral. And on the right-hand side, you have this. Gamma 2 and gamma 1 are certain powers, and I'm not going to details for this. But this also holds in the vectorial case, provided this unavoidable quasi-diagonal assumption is got. So this condition is universal also in the non-uniformly elliptic case. So essentially, ln1 is a universal condition to get that the gradient is bounded, both in the uniformly and in the non-uniformly elliptic case. There's no difference whatsoever. What it counts is the divergence form as an effect of Sobolev embedding. And this result has been extended with a slightly improved boundary by Bell and Schaffner very recently, and has been extended in another very interesting paper by Cristiana De Filippis and Mirko Piccinini in this journal here. But the essence is that this condition is universal both in the uniformly and in the non-uniformly elliptic case. No difference whatsoever. Okay, how do we prove this? We give a new way of proving a priori Lipschitz estimates that makes use of certain nonlinear potentials, And it provides a very straightforward approach when f is equal to 0. And in a sense, this approach allows, in the spirit of what we have seen at the beginning of the talk, allows to reduce the non-uniformly elliptic setting to the uniformly elliptic one. There is essentially no difference. Essentially, we reduce everything to the Poisson equation in a sense. And that's why ln1 appears everywhere, because there's no difference now between these kinds of operators and the Poisson equation, as we have seen at the beginning. Okay, what about this estimate that looks very bad, apparently, but let's see what this estimate gives you back, because you see, this estimate covers both the case of PQ growth conditions, but it also covers the case of exponential growth conditions. So if you get an exponential functional, this is okay. This is again okay. Essentially, if you are in the standard case, the previous estimates, if you write down what these quantities are, you get this natural estimate, which is the usual estimate for the P-Laplacian equation. So the previous estimates gives you back the classical one. In the PQ case, where G1 is T to the P minus 2 and G2 is Q to the P minus 2, then the previous estimate gives you back Marcellini's estimate. And you see, if in the second estimate you get P equal to Q, you get the first one up to F is equal to 0. So the previous estimate is essentially the natural estimate you want to get. What about when you also add coefficients? When you also add coefficients and you get, for instance, an exponential functional of this type, this is a recent result by Cristiano De Filippis and myself, then you get, once again, that F in L1 is the usual assumption, and on C1 and C2, you just prescribe that they are Sobolev differentiable with any D larger than N. Prescribing Sobolev differentiability was done several times in the literature. For the first time in the PQ case was done by Marcellini, Eleuteri, and Mascolo, I guess. Now here we prove that, for instance, if you have a local minimizer of this functional with coefficients, so with the exponential growth, once again, the condition on the right-hand side F is always the same. There's no difference, while you have to assume just a bit of Sobolev differentiability on the coefficients that allows, by Sobolev-Morey, that C1 and C2 are Hilbert continuous. So this doesn't break the rule that in order to get that the gradient is bounded, coefficients must be at least Hilbert or D continuous. Here we require a bit more. And so these are just a universal condition extending in all kinds of possible directions this philosophy that the right-hand side, I mean, the conditions on the right-hand side are independent of the operator. Ellipticity is always sufficient. And then you can extend this to any combination of exponentials, putting coefficients wherever you want. There's an F missing, of course, here. F is missing here. So any type of coefficients then get you that, that any exponential, I mean, any type of exponential is okay in this setting. And you see, this is not easy to get because you see, when you make, for instance, how do you prove that U is bounded or U is continuous or Hilbert continuous? Usually you do by perturbations. So you freeze a point and then you make perturbations around the point. Here, if you make perturbations, then you lose integrability because there is no delta 2 condition. So it's not easy to deal with the exponential functions. And so this extends the classical results of Marcellini in the 90s for exponential functions. And once again, F is in L1 is always the universal condition. And in particular, if you go back to the uniformly elliptic case and you consider these kinds of equations, which are uniformly elliptic by these assumptions, then both the coefficient, the derivative of the coefficient, and F must be in the same ln1 because they scale, formally developing the divergence operator in the same form. And this is a new condition also in the uniformly elliptic setting, because the classical condition on coefficients in the uniformly elliptic setting is that these coefficients are assumed to be Dini continuous. Here you do not assume that they are Dini continuous, but you assume that the derivative is in ln1. Assuming that the derivative is in ln1 implies that C is continuous, but not necessarily Dini continuous.
Здесь опечатка, Саш, переведи вот формулу V, там H' делить на...
Sasha, what are you talking about?
Больше И там... Подожди, one moment.
Он момент, I will translate. Чего тебе перевести?
Вот там опечатка у него в этой формуле, где больше И, какой-то И не поэтому, минус единички, там меньше S, вот там.
Нет, просто два числа.
А что такое И там непонятно? Вот
Число.
Число, что ли?
Okay. Rosario, my colleague asks, what is I in the second formula? I think it is just a number. No,
This is
in the second.
This is a function. This is a function.
Yes, and нет. I in the second formula.
It's a number. This is a number.
It's a number. Yes.
It's a number.
Okay.
Yeah.
Thank you.
It's a lower bound of this quantity. It's a number, yeah.
Okay, thanks.
Something like inferior bound, I mean. there is a superior and inferior bound.
Exactly,
That's
right.
why they are I and S.
Yes, yes.
Okay.
Okay. Okay, as a corollary of the previous results that we obtained in this new paper with the Cristiana De Filippis, there is for the first time, I think, the sharp condition on obstacle problems guaranteeing that minimizers are Lipschitz. So in all the previous cases, and this result is new already in the uniformly elliptic setting, already for the P Laplacian, this result is new. If you do consider a functional of the type we have seen before, so P growth, PQ growth conditions, so both in the uniformly and in the non-uniformly elliptic setting, and not even in the exponential setting, if you minimize this functional with this lower obstacle, then if the second derivatives of the obstacle belong to ln1, then the gradient is locally bounded. And this applies to any functionals we have seen before, any functional. So either you have P growth or PQ growth or exponential growth, or any combination of the exponentials as we have seen before. Okay, how does this proof go? We use the following linearization principle. That is, you can rewrite the Euler-Lagrange equation of an obstacle problem in the following sense. Divergence of the left-hand side of the, divergence of this quantity, which is the usual quantity, is equal to let's say a distribution function of theta of x, which is times the divergence of this object, which formally involves second derivatives of the object. And this is only supported on the contact set. So outside the contact set, you are a solution of just any of an unconstrained problem. And this all only lives on the contact set as usual. Now, if you develop the right-hand side and you keep in mind that the gradient is in L infinity because the second derivatives are in ln1, then you get the following upper bound on this quantity. Now, this object is bounded because d phi is bounded, d psi. This object is bounded because d psi is bounded. So this is in ln1 if this is in ln1. So f is in ln1, and then you can apply the previous results. So this is, as far as I know, the first optimal regularity conditions on solutions of obstacle problems, giving you that the gradient is bounded when you under optimal conditions on the obstacle, and this applies to any functional whatsoever, independently of the growth conditions. Even exponential or any combination of exponentials are covered by this theorem. Okay.
Excuse me, one question here. It is not important that psi is a lower obstacle, surely.
No, it's not important. You can also consider a double obstacle. You can also consider a double obstacle problem, because then in the double obstacle problem you get two terms. This one, you get the contact set both on the upper and the lowest obstacle.
Okay. Thank you.
I mean, you can also consider, double obstacle problems. These are being considered.
Okay, thank you.
The important thing is that the observation is that you can linearize. This linearization is possible when the second derivatives are in ln, and they are in ln because they are in ln1, which is smaller than ln, and then you can apply the previous result by just expanding formally the divergence of the right-hand side. Okay. Now, these are some of the results I wanted to talk about, and now let me give a simple shots on how we prove these results. These are shots from the potential theoretic methods. So I'm going to be rather sloppy here, just to give a general principle covering all the cases. Sometimes in certain results can be refined by applying the same principle in a more accurate way. But let me sacrifice generality to, let's say, to exposition. But almost all results are sharp here. Okay, these ideas appear essentially in 3 papers. The first one is with Lisa Beck that we have seen before. The second one is with Cristiana De Filippis, and also the third one is a preprint. And this is essentially what I was talking about before. I mean, I'm going to give a general approach. Okay, let me take an elliptic equation of this type. So a linear elliptic equation, which is uniformly elliptic. Lowest eigenvalue, highest eigenvalue, no problems on that. Oh, there's a typo here. This should be, this should not be here. So partial is not here. So this is bounded coefficients and elliptic coefficients. Now, if you write down the standard Cacciopoli typing equality on level sets, the standard Cacciopoli typing equality on level sets is this one. The gradient of the lowest rancation of V is less than or equal than this stuff, and this is something that Lagichenska and Togaltseva taught all of us after the Georgi, and then the right-hand side contribution is the following. And this can be easily obtained by testing. I don't think I have to explain this in St. Petersburg. I mean, this is very, very standard. Okay, in particular, if you have this, if you properly choose tau and sigma. And if f is equal to 0, you get the usual one. You know that from the usual one, from the last one, by the Georgi's or the Georgi's iteration, essentially, you get the following upper bound on the L infinity norm of V. The passage from this to this is the Georgi, and it's again something I don't think I have to explain in St. Petersburg. This is the Georgi's iteration. This is a function that belongs to the Georgi class, then satisfies this upper bound. Actually, it's a soup. It's a soup, and then you prove that minus V is also a solution, and then you get this. Okay, a function satisfying this gets this. You get this with the soup, not with the L infinity norm. But if you know that D satisfies this equation, then minus V also satisfies a similar equation or the same equation, and then you get L infinity bound. Standard. Okay, now let me recall the full horrible definition of Lorentz spaces. This is LS gamma, where S and gamma are allowed to vary between 0 and infinity. It is what it is. And this is essentially the decay of these level sets measured by this R measure. And you can rewrite via Fubini by using rearrangements. Okay, as I told you, Lorentz spaces coincides classically with Lebesgue spaces. The second index is stunning the first one in the following sense, and the first one dominates always over the second in the sense specified here. And you can also rewrite the Lorentz norm in, okay, you can express it in this equivalent definition, which provides a real norm. The previous quantity was not a norm, actually. It's a quasi-norm. Okay, this quantity, this very horrible quantity, is a potential of having Mazia-Wolf type. It's a nonlinear potential depending on these parameters. Actually, there are 3 parameters expressed for readability as 4. And this is the potential we are going to consider. Why this potential is relevant? Because for suitable choice of the parameters that you are seeing here, this coincides with Riesz potentials and Wolf, or having Mazia-Wolf potentials. In fact, this is the classical Riesz potential. This is bounded by this quantity, and this is P1111. So Riesz potentials of the type we have seen that are useful to bound the gradient with, they can be expressed like a particular instance of P, of capital P. And then also having Mazier-Wulff potentials can be considered as these potentials. This applies when f is a function where this is the integral of the function f over the ball B rho x0. So these are the potentials that we are going to consider. Now, the crucial observation is the following one, that this potential is bounded when its argument belongs to this Lorentz space. So where this is coming from, it's a three-line lemma coming from definitions. So there is absolutely nothing deep here. It's just something that you can check using the definitions and also the rearrangement type of definitions. Using the previous ingredients, then this can be done in 3 lines. This is just to say that when f belongs to this Lorentz space, then this potential, this awkward potential, is bound. Okay. Now let me go back. Let me go back to this. And this is a way of rewriting the Giorgi's iteration after the work of Kilpelangen and Mali, and after the work I also did with Tuomo Cusi. And it's a way to rewrite the Giorgi's definition when you shrink not up from one ball to half of the ball, but up to 1 point, straightforward up to 1 point. So this lemma tells you the following. If you satisfy this almost reverse Elder inequality, reverse Elder because this chi is larger than 1, plus this additional term, then you can pointwise bound V by the usual average, plus the potential of F. So this is the novelty. This is, in a sense, a result of Lagrange-Riemann type. If you belong to a certain class, then you get this bound. This is something we proved. This can be proved. This can be found in this paper with Cristiana De Filippis, for instance, and also with Lisa Beck. So in some sense, this extends the idea of being at the Giorgi class means being bounded. So being at the Giorgi class, that implies a certain reverse Elder inequality, plus an additional term gets this bound. Now let's see how we can apply this to the setting of linear equations we have seen before. We use this Cacciopoli inequality. Then by Sobolev embedding, it is standard to use Cacciopoli after Sobolev embedding after Cacciopoli inequality, we get this. So this is satisfied by this equation. This is satisfied by Sobolev embedding, and where this is the Sobolev embedding exponent. Now we are able to apply previous lemma, because the previous lemma tells us exactly that you have a reverse inequality plus an additional term with a radius. And now there's a reverse Elder inequality plus an additional term with the radius. Now we apply the previous lemma and we get the following bound. Of course, here we are using that both V and minus V are solutions to the same equation, because the equation is linear. It's essentially subsolution and subsolution, supersolution and subsolution property. So applying the previous lemma gets you this, and applying, and if n belongs to Ln over to 1, then we can apply this other lemma. As a result, we get that if f belongs to Ln over 2, 1, then V is in L infinity. And this is sharp. This was already known in the literature, but this is a way to find back the previous results with this lemma. So let me summarize. We have a pointwise, so we have a right-hand side version of the Cacciopoli inequality. Then we have a new version of the Giorgi's iteration that makes a suitable nonlinear potential appear. And then when you know where f is, you know that this object is bounded, and then you can conclude with the L infinity property. So this is a class, this is
Professor, One, dear Giuseppe, it
Yes.
is in
Так, Юр, это самое, хочешь спросить, давай я переведу, так проще.
x нулевая точка Лебега или вообще там, или можно сказать S суп, вот я хотел спросить.
Yeah, okay, the question is x0 a Lebesgue point?
Yeah, this also at every Lebesgue points, but by approximation you can put it is everywhere because you can take everything L infinity. Here we have let's say this is not a problem because you want to know where. I mean, if this holds at every Lebesgue points, it also holds almost everywhere. So this is not a problem. But this you are correct. This also at every Lebesgue points. Okay, this is an application in the classical setting. Now, Nina, the cat this time, recommends to carefully look at the constants. Now we do something that is usually never done in the literature. So we take this lemma, and you see in this lemma, usually there are constants here, and the idea is that who cares about the constants? Now we care about the constants. Because we have this. We have an upgraded version, and we look at a point where usually nobody looks at. Always, I mean, this is recommended by Nina. So we carefully look at the proof, and we discover that if you start with these constants, you end up with these other constants. This is usually hidden in the proofs, but now we take care about these constants. Now you wonder why we want to take care about these constants. Let me go on. Now let me go back to the standard PQ setting. So we have an equation whose lowest eigenvalue goes like P minus 2, and highest eigenvalue goes like Q minus 2. Okay, now we want to do something similar as we have done before. Now, if you differentiate the equation and you apply a certain proper variations of the so-called Bernstein inequality, we end up with the following hybrid Cacciopoli type inequality. G is a suitable expression of the gradient, which is actually the following one in the PQ case. So you get that the gradient in the PQ case we are considering, the gradient of this quantity, and here you see the subsolution property, because usually when in the P Laplacian case and the right-hand side is equal to 0, this is a subsolution. Now, this is not a subsolution because there's a right-hand side, but it still satisfies a Cacciopoli type inequality. So we have the following Cacciopoli type inequality, which is the following one. The gradient of this quantity is bounded by this plus this, where M is essentially the L infinity norm. So what are the features of this inequality? The features of this inequality is that this inequality is homogeneous in the gradient. So the same power of the gradient appears here, which is 2p, that appears here, 2p. So why do we have a homogeneous inequality, which is typically in uniformly elliptic problems, in a non-uniformly elliptic problem? Because we put everything about non-uniform ellipticity here, m to the q minus p, and we are putting m here. So m is something about the gradient itself. Now, starting by this lemma, this can be found in these papers with Beck and De Filippis, we can apply Sobolev embedding theorem in the following way, as before. And now we get this reverse type inequality. You see, this is power 2 chi, and chi is larger than 1, power 2. Here you have, once again, something which is bad. And now you apply the previous lemma. Now, you see, you want to keep track of capital M, and therefore you apply this lemma. And this is t equal to 2 with this choice. So you see, using this trick, you get for a non-uniformly elliptic problem, a Cacciopoli type inequality of Bernstein type, which is typical of uniformly elliptic problems, putting the whole information about non-uniform ellipticity in this multiplicative constant here. Now you apply the
Rosario,
Yeah.
am I right that a bit more formally you take some approximation which is
you take everything. Yeah. Okay. This is formal. This is everything done here is formal. This is a good question. Everything done here is formal. Then you have to embed this in an approximation procedure, and you just prove this as an a priori estimate for more regular solutions, and then you pass to the limit.
Okay.
But let me concentrate on the core, which are the a priori estimates. Okay, now you get this lemma, and capital M is here. Now you apply the lemma with the precise dependence of the constants, and you come up with this. So the idea is that you don't lose anything about capital M here. And once again, if F is in Ln1, then this potential is locally bounded. So you get this. Now you still want to get rid of capital M, because capital M is like the L infinity norm of the gradient. And now you fix a ball, B capital R, and then you take two concentric balls, and then you apply the same estimates of small balls in the annuli. You apply the previous pointwise estimate on small balls in annuli. These balls are centered in beta 1 and have radius in order that everything does not escape from beta 2. And with this choice of M, of course. So you get this. Now you want that this is less than 1. Actually less than P, and you want that this is less than P. So you can apply Young's inequality to get this. And then you can conclude with this iteration lemma to reabsorb this. And then you get this estimate. In particular, when F is equal to 0, you get back Macellin is bound. So in this way, we have reduced any non-uniformly elliptic equations of power type to uniformly elliptic equations. Why? We have written a Cacciopoli type inequality, which is homogeneous, and which is, you see, if Q is equal to P, this doesn't appear, and this is the standard Ueltsev-Uhlenbeck Cacciopoli type inequality for the subsolution. Otherwise, you get this contribution from non-uniform ellipticity and this contribution from the right-hand side. Once you get this, you make the iteration and you control the constants. So you look at by following Nina's, this time, recommendation, you look at the precise dependence of the constants, and the miracle happens because you get exactly the bound that you were looking for. Last but not least, how do you derive this Cacciopoli type inequality? By differentiating the equation. Now, if you have coefficients, and coefficients are Hilbert continuous, so you are in the range of Schauder theory, you cannot differentiate the equation. So the idea is that you make a fractional differentiation of the equation, and you write down along the same scheme a fractional Cacciopoli type inequality for equations of this type. And now on the left-hand side, you don't get the full derivative of u to the p, but the fractional derivative of u to the p, plus these other terms. And then you get further bounds on these exponents in order to make the same argument, the previous argument work, and then you can go on up to the very end. And I think I would stop here. Okay, do I have still 3 or 4 minutes?
Yes.
Okay, so let me just stress the general principle. The general principle is that you have a Cacciopoli type inequality here that does not involve first derivatives, but fractional derivatives. But once you have this, and this is along the Hilder continuous dependence on coefficients, you can still run the same mechanism because you have a Sobolev embedding in the fractional sense, and then you can write down with new exponents. And this leads to establish the long-standing problem of validity of Schauder theory in the non-uniformly elliptic regime, because now you can prove Schauder estimates for non-uniformly elliptic equations, and this was a very long-standing open problem. In the whole literature, if coefficients are non-differentiable, you cannot prove that the gradient is bounded, and eventually that is locally Hilder continuous. Now, this is done via this renormalization, via this de Giorgi's approach. As an encore, let me give a fast proof of this result using a result of the previous type, this time using Moses iteration, but without a right-hand side, because for right-hand side we use de Giorgi's, we need de Giorgi's iteration and nonlinear potentials. But similar ideas when the right-hand sides are not involved can be used to prove gradient estimates using Moses iteration. And now let me give you another application of the same general idea. So the idea is to reduce a non-uniformly elliptic equation to a uniformly elliptic equation. So I'm getting, once again, PQ growth conditions, P eigenvalue, P lowest eigenvalue, and Q higher eigenvalue, and dependence on X2. And I want to prove that the gradient is in L infinity under this bound. This bound is sharp, so it cannot be improved. It cannot be improved this time. In the non-autonomous case, the sharp bound is known, and it is this one when you have differentiability of coefficients. Okay, when P is equal to Q, you do one simple thing. You see the lowest eigenvalue, there's a constant here, L. You run, when P is equal to Q, you run Moses iteration, and Moses iteration is the following estimate. And once again, we are making explicit the dependence on L, this capital L. So the whole point here is that you prove Moses' scheme paying attention to the dependence on L. And if you are careful enough, this is the best dependence on L you can get. Okay, now you do something similar as before. If you are on a ball beta 2, then the previous conditions can be rewritten in the following way. If Z is the gradient variable, then you can put K of du outside. And then you can make the problem with the P equal to Q growth, because you just plug outside the ellipticity ratio. This is exactly the ellipticity ratio. So you plug outside the ellipticity ratio in L infinity norm, and then you get a uniformly elliptic equation. Now you apply the previous inequality with this new L. This is the new L. If you apply it, you get this. So you see, you have done Moses iteration in the standard case, but with careful dependence on the constants. Then you applied Moses iterations in the non-standard case, but taking this out, and this is what you get. Now you prescribe that this exponent is again less than 1. And you apply Young's inequality. Because this exponent, Q minus P times N over P, is less than 1, provided the upper sharp bound on Q over P is satisfied. You get Young's inequality, and you end up again with the previous lemma, and then you get an easy a priori estimate on L infinity. So conceptually speaking, what you do is to get the non-uniform case from the uniform one, shifting everything in the sharp dependence of the constant. Okay, I think this is a good moment to stop. Thanks for your attention. By the way, this also gives the sharp bound, and thanks also from Nina.
Okay.
They were my cat.
Questions, please, comments.
What is the cat? Your cat.
What do you mean? What is my cat?
No, he means, is this your cat?
Yeah, this is my cat.
Mhm. Yeah. In fact, maybe I have a strange question, maybe terminology. I thought that the George idea was integration with respect to level sets, and the Moser idea is the iteration by
Powers, yeah, over
by
powers.
powers, but in some moment you wrote powers but said the George.
No. Okay, the George's idea is that you first write an inequality on level sets, but then you have to gain a geometric improvement on these level sets, and therefore you have to get fractional embedding, or Sobolev embedding, sorry, and this Sobolev embedding gets you this improvement, and after this improvement you can run the
Okay.
So Moses improvement goes straight away to L infinity. Here you go from L2 to L2 chi, and then you iterate over level sets. So you go to L infinity over levels rather than on powers. But you still need one power, and it's the same improvement you get in Moses.
Okay.
I think that Italian mathematics don't like Moser.
I think that amongst the people here there is Paolo Marcellini. I think that at least Paolo likes Moses very much. Paolo, is this correct?
Yeah. I have seen. I heard your seminar. I think that it's clear your method. The only problem is that then you need maybe an approximation, because this gives an a priori estimate. Then you have to prove for the real solution.
No. But this you can do by approximation.
Yeah, by approximation. So still, there is some material to do, but this is very, very clear and very interesting, this approach.
Yeah. Okay. If not, if nobody has more questions, Жень, ты что ли? Okay, then let's thank speaker again.
Thank you very much.
Thank you very much. Thank you.